Welcome to Online Precalculus. Today, we're going to cover section 1.6, transformations of functions. So our objectives for this section are to recognize graphs of common functions, use vertical shifts to graph functions, horizontal shifts to graph functions, reflections to graph functions, both in the x and in the y. We're going to do then vertical stretching and shrinking to graph functions, horizontal stretching and shrinking, and finally graph functions with all these transformations, a sequence of transformations. So first, let's go over the 7 common functions in algebra. So the table below is going to show each function's graph and the list of its characteristics. So what we want to do, what we want to take away from this is when we see a picture, we want to know what the graph of that picture, what the equation of that picture is going to look like, what the general or what the parent function of that picture is, and what are the basic properties of the parent function. And here are the first 3. We have a constant function, which is just a flat line. The function equal to a number, okay? Sort of like something like that. Y is equal to 3. In this case, it's like 1 and 2/3 or so, okay? In this case, the domain is all real numbers. The range is just one number, and this function is constant on the entire interval, negative infinity to positive infinity. It's also even. Remember that even functions are defined as a function where a negative inserted into the function gives me back my original function. And it also means that it is symmetric about the y-axis. The next function is my identity function, or the parent linear function. Okay, and this function, right, domain all real numbers, range all real numbers, is always increasing. This function is odd, which means that f of negative x is going to equal negative f of x. This also means that it is symmetric about the origin. So that means that any point on this graph also has the opposite point on this graph. So that's 1, 1, and we have -1, -1, 2, 2, -2, -2. That is the characteristics of an odd function. Okay, so these two are our basic lines, right? So we have a horizontal line and we have any other line right here. So we have the parent linear function. And from these, we can make all the other different types of lines out there. Next, we have the absolute value function, which kind of looks like a V. It's going down from left to right, then it hits the origin, and then it bounces back up. The domain is all real numbers. The range, however, is from 0 to infinity. Okay, so the function doesn't go any lower than 0. Decreasing on the left, increasing on the right, and it is an even function. And I would argue that the most important point on that function is that point right there, the vertex of the function. Okay, the next 3 are my quadratic, square root, cubic, and cube root. So when we go about graphing all of these, you kind of have to know what the shape of the parent function is going to look like. So here we have our vertex, which is 0, 0. We have a point there, 1. 1 squared is 1. We have a point off this graph, 2, 4. We have another point, 3, 9. Right? These are just plugging inputs into x squared, into my parent function. Okay? And because this is even, all these points repeat on the left side of the function. Okay? So if we can remember if we can understand what the function is going to look like when we make a transformation, when we move this function to a different spot, this pattern is still going to be the same. We're going to have a vertex. That's going to be the middle of the function. 1 point to the right of it, we're going to go up 1, unless, of course, we stretch it out. 2 points to the right, we're going to go up 4. 3 points, we're going to go up 9, right? It's just the input squared. Okay? And then you can see the characteristics there. Domain is all real numbers, range 0 to infinity, decreasing from negative infinity to 0, increasing from 0 to infinity, just like the absolute value function, and even. Okay? And then we have the square root function, which is similar to the quadratic function, only it's on its kind of on its side. And look at the points on this graph: 0, 0, 1, 1, right? But this is the square root function. So if I plug 2 in there, I get a square root of 2. I don't really like that. 3, I don't like that. But if I plug 4 in, I get 2. If I plug 9 in, I get 3. So you notice that these points are reversed from the quadratic function. Okay, that is because they're inverses of each other, with something that we'll cover in a later section. This is our first function that is domain limited. Okay, the domain is only from 0 to infinity. Range is from 0 to infinity as well. It's always increasing, and it's neither even or odd because it's not symmetric. This is the only one of these functions that is neither even or odd. The next two are both odd. And they have a similar relationship. So the standard cubic function, right? We have this middle point right here, this inflection point. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. So those would be the points on this graph, as well as their opposites, because this function is odd. It's always increasing. Domain negative infinity, positive infinity, range negative infinity, positive infinity. And then when we look at the cube root, we see the similar pattern that we had between quadratics and square root functions. We have our inflection point, 0, 0. We have our next point right here, 1, 1. But then this function goes, it doesn't go up very high because we're taking the cube root. I don't want to take the cube root of 2, 3, 4, 5. I only want to take the cube root of 8 because that works out to a nice point that can be graphed. I don't want to take anything until I get to 27, and then that'll give me a nice point of 3. So again, these two functions are inverses of each other, so they behave similarly. So next, let's start moving these functions around. And the idea is that once we know what these all look like, okay, before we even graph them, just by looking at the equation, if we know where they start, we can start to manipulate these functions and move them to different spots in the graph a little bit easier. Okay, so let's start by looking at three graphs whose shapes are the same. These three parabolas in the picture. Okay, the black graph is the standard function, the parent function, f of x is equal to x squared. The blue graph on top is x squared plus 2, and the red graph on the bottom is x squared minus 3. Okay, notice what the effect was of these two additions to the function. If I added 2, it made the blue go up. If I subtracted 3, it made the red go down. Okay, so we look at the red graph. Okay, and also notice that in both of these, we're adding it and subtracting it to the outside of the function, to the output of the function. We're not squaring the 2 or the 3. We're squaring my input first, whatever it happens to be, and then we're adding 2 or subtracting 3 from that answer. So in general, if C is positive, we're going to move, this is C, the thing I'm adding to the function. If it is positive, we're going to shift the function up, and if it is negative, we're going to shift it down. And there is my formal definition for vertical shifts. Again, notice where this number is. It's very important because the horizontal shifts, those numbers are going to be in a different place. So if I add C to the output of the graph, output of the function, the graph is shifted vertically up. Subtracting C shifts it down. Notice that every point on the graph just gets shifted up C units, and there they all get shifted down C. So there's a couple of different ways to graph this, right? If we have our formulas, I could jump right to this one, and I could make a table, plug in some x's, and get some output points. But if I start with the parent function, which looks like this from the last page, I missed this one a little bit. Yeah. Okay, so if I start with those two, this tells me all I have to do to get my new graph is to shift, that didn't work, is to shift this, oh, let's just go, is to shift this down 4 points. Let's do it with red. Okay, so now every point on the graph gets shifted down 4. And now I have a graph that looks like kind of like that. Okay? Every point on the graph gets shifted down 4. Right? And I didn't have to make a whole table. I didn't have to go and calculate a bunch of different points for this because I knew what this function looked like. I knew that it has a vertex of 0, 0. I know that it has a slope on the right branch of 1, a slope on the left branch of -1, because I've graphed the absolute value function enough to know things like that. Okay. Let's try again. So use this graph to get this one, plus 3. So again, instead of shifting it down 4, 1, 2, 3, we now shift every point up 3. And this still has a slope of 1 on the right and still has a slope of -1 on the left. And there's my graph shifted up 3. Okay. Horizontal shifts are a little bit different. So let's go back to x squared, the standard quadratic function, the quadratic parent function. And if we look at the picture, we can see that the standard one is in the red. Okay. Adding 2 to the inside of the function shifts it left. Subtracting 3 shifts it right. Okay. This is not what, this is a little bit backwards of what you think it would be, because adding something shifted in the positive direction, right, up, for vertical shifts, subtracting something from the outside shifted something down, right, in the negative direction. But for horizontal shifts, it's going to be backwards. This is strange. Subtracting 3 in the domain shifts it to the right. So if you look at this table, we can sort of prove that this is true. Let's focus on 0. Okay, so 0 squared is 0. We can see that, right? That's my vertex coordinate. Okay, but if I'm plugging it into this function right there, in order to get 0 to be squared to give me 0 as an output, I need to have 3 as my input. 3 more. 3 to the right, not to the left. Right? If I were to plug -3 into there, that would give me positive 36. Okay, so not what I'm looking for. Okay, and that's explained right down here. So look at the red graph again and the blue graph, and we can see that the red graph is shifted left and the blue graph is shifted right, which gives me my general rule for horizontal shifts. Okay, if C is added to the inside of a function. Now, how do you tell the inside? For the parabola we just looked at, it was the parentheses. Right? You can tell it was the inside of the function because it's inside of the squared. For absolute value, it's inside the absolute value. Square roots, it's under the square root. Lines is really harder to tell, and you don't really need to go all that in depth with a line. But when we're talking about any of those other functions, it has to be inside the thing that makes the function special, right? The squared, the cube, the square root, the cube root, the absolute value signs. Okay, adding something shifts it to the left, subtracting something shifts it to the right. All right, so let's use the graph of the square root of x to get x plus 5. Okay, the square root of x plus 5. So first let's graph the square root of x. And I can do that fairly easily by just plugging in numbers that have perfect squares. 0, square root of that is 0. 1, the square root is 1. 4, I don't want to plug in 2, I don't plug in 3, right? 4, the square root is 2. 9, the square root is 3. And I get my graph of the parent function. Okay. So now, to graph x plus 5, I know that this plus 5 shifts this graph to the left. A positive shifts this graph to the left. So I'm going to focus on the starting point right there. Instead of starting at 0, 0, it's going to start right there. I'm going to shift each of these points, every key point that I graphed, I'm going to shift it 5 to the left. And watch the pattern that sort of happens with them. Is 1 to the right of 5, you go up 1. 1, 2, 3, 5 to the left of this point. 2 to the right of 5, well, I don't know the square root of 2, but 4 to the right of 5 would be my point for 2. 1, 2, 3, 4, 5 points to the left of the other point I graphed. And so the same pattern happens, it's just everything is shifted left. So if I know the starting point, I could use those same inputs and outputs, just starting at a different place, starting at -5 instead of 0. Okay, and so then 9 points to the right of 5 gives me a 3. And even I can graph one more of this now, because 16 points to the right gives me a 4, right? Because 16 squared is 4. Yeah, this is 11, but if I plugged 11 in there, 11 plus 5 is 16. Square root of 16 is 4. Okay, so now I have my graph. Ooh, not perfect. Let's try again. Now I have my graph. It doesn't look quite exactly the same because we're looking at more of it. Okay, so if I wanted to move this over, which I'm having trouble doing, nope. Okay, so if I wanted to slide this over, if I wanted to move the black line over, you would see that they do match up. Okay, let's try another one. Use the square root function again to graph x minus 4. So here's my square root function, 4, 2, 9, 3. There's my square root function. And now I know I'm going to shift this right 4. Right 4. Right 1, 2, 3, 4. Go up 2. And from this new starting point, do I have room to go 9? 5, 6, 7, 8, 9. Just barely. Okay? And I get my graph that looks like that. Again, they don't look perfect, but if you were to superimpose them right on one on top of the other, they'd look about the same. Okay, except the red one is much shorter than the black one because I ran out of room. Okay. Now, some functions can be graphed by combining horizontal and vertical shifts. These functions will be variations of functions whose equation you know how to graph, like quadratics, cubics, square root, cube root, all the functions in the past. Except we're going to do more than one shift. We're going to shift it up or down and left or right. So we're going to do two things at once. Let's see what it looks like. Okay, so we're going to use the standard parabola. Let's just graph that. 1, 1, 2, 4, 3, 9. And these can all reflect because this function is even. Then, again, if I know the starting point, I can graph this fairly simply. Left 1, down 3. Left 1, down 3. There's my starting point. So then I can take every single point and move it left 1, down 1, 2, 3. Left 1, down 1, 2, 3. Or I can use the property of the parabola again And from the vertex point, from this point right here, count right 1 up 1, right 2 up 4, right 3 up 1, 2, 3, 4, 5, 6, 7, 8, 9, and put a dot there. And you can see that moved this point left 1, down 3 as well. All these points get reflected across an axis of symmetry that happens at the vertex. It's the middle of every parabola, and we get our curve. Okay, so these two graphs are exactly the same shape. They just start and then finish in different positions. Well, they keep going on, but let's try the checkpoint. Okay, so let's go back to our square root function. Here's the original. 4, 2, 9, 3. Okay, there's my square root function. A little flatter this time, but what are you going to do? And we move the vertex, or not the vertex, we move the starting point right 1, down 2. There's my starting point. Every other point here can be moved right 1, down 2. Right 1, down 2. This one, right 1, down 2. Okay. The other way to do it is to, from the starting point, count right 1 up 1, right 4 up 2, right 9 up 3. Okay. Just like you would do for the original function. And there's my new function. Okay. Next comes reflections. If you look at the black in the graph and the blue graph, you can see that they look exactly the same, only one goes up and one goes down. This shows that they are reflections of each other. And notice their formulas. One is x squared, one is negative x squared. Okay. And these are reflections around the x-axis. So when you reflect something in the x-axis, the y-coordinates are opposite. So we have 1, 1. Down on the blue graph, we have 1, negative 1. The input is the same. The output switches from positive to negative. Okay. So in general, when we do this, y equals negative f of x reflects the graph around the y-axis. Okay, because these two equations show that. Okay, and that's my general rule here, is the graph of y is equal to negative f of x is the graph of f of x reflected around the x-axis. Notice where this negative sign is. It is on the output, the outside of the function. Okay, if I had put it in the inside, it would have reflected it in the y-axis. Okay, and that wouldn't have done anything here because this function happens to be symmetric. Okay, so if I want to use the cube root function, so my cube root function 0, 0, 1, 1. I don't want to graph any number before 8 because 8 is 2. And then I need to go all the way to 27 to get 3. So I'm just going to go the other way now. Negative 8, 2. And so here's my graph of the cube root function, sorry. If I reflect this in the x-axis, it means that every point gets flipped across the x-axis. 0 stays the same. But instead of 1, 1, now we go negative 1. Instead of 2, 8, this becomes 2, negative 8. The input stays the same. The output changes sign. Instead of negative 1, negative 1, we get negative 1, positive 1. Negative 8, positive 2. And so now my graph looks like that. And you can see that it is a reflection across the x-axis. Okay. We can do the same thing with my absolute value function. Here's my parent function. The intercept stays the same, but every point gets reflected across the x-axis. And so now my graph looks like this. And yes, all the outputs from the absolute value part are positive, but that negative in the front there is what makes those outputs negative. It's also possible to reflect about the y-axis. Notice where the negative is this time. So now we have the negative on the inside of the graph, in the inside of the function, to the input. Okay, this is a reflection about the y-axis. And so every point, xy is going to change to negative x, negative y on the graph. We're going to flip them side to side. And that's why this function, right, the first one that we graphed, x squared, right, that reflected in the x-axis, which made the parabola go upside down. If we had tried to reflect it in the y-axis, we'd have had to write it like that. And then that wouldn't have done anything because now we're squaring the negative sign and it's just going back to positive, which is why a parabola wouldn't reflect around the y-axis because it would look the same. Okay? So let's try this function. Notice where, well, let's graph the original. 9.3, here we go. There is my first function. We'll go with red here to graph the reflection across the y-axis. This point stays the same, 0, 0. Instead of 1, 1, we turn it to negative 1, 1. The x value changes. Instead of 4, 2, it becomes negative 4, positive 2. Instead of 9, 3, it becomes negative 9, positive 3. There is a reflection across the x-axis. We could even reflect this across the x-axis if we wanted to in blue, but that is the way we would have to write this function. Now, my graph would look like this. Okay? And then if we want to get really crazy, let's go with green, we could graph a graph that flips both. And that would look kind of like that. Okay, so now we're reflecting x and y. So that means I'm going to either reflect the blue one across the y-axis or the red one across the x-axis, and we would get something down here. Pretty cool. We're only going to do one for this one. Okay, so we're going to start with the cube root function. Again, we have to go all the way to 8 to go up to 2. And the opposite, negative 8 to 2 there. So there would be my starting function. Let's go back to red. Now every point gets reflected across the y-axis. And because this is the way this function works, is this would really look the same as flipping it over the x. Okay? Just flipping over the y and flipping it over the x would kind of look exactly the same. Because negative third root of positive x is going to be the same thing as the third root of negative x. Just the way the cube root function works. Okay, so next is stretching and shrinking. So morphing is going to do more than move the image horizontally, vertically, or about an axis. It is going to change it into a different shape. Horizontal shifts and vertical shifts and reflections don't change the shape. They just move the thing around. They remain rigid and proportionally the same. Yeah, they're in a different spot, but they're basically the same shape. You can see from these three graphs of the parabola that the blue one is skinnier and the red one is a little bit wider. Okay? So for vertical stretching and shrinking, you are going to multiply the outside of the function by a number. If that number is bigger than 1, you are going to stretch the function by a factor of c, whatever number you're multiplying by, right? Whatever number is in the front of the function. If the number is in between 0 and 1, you're going to shrink the function by a factor of c. And we are shrinking it vertically. Now, we say between 0 and 1, not equal to 1 because 1 wouldn't do anything. And we don't include negative numbers because negative numbers are going to be reflections. It's going to be something different. Okay? So when you stretch a function, the tops get higher, the intercepts stay the same. The x-intercepts stay the same. When you shrink the function, the tops get lower, it gets pulled closer to the x-axis, but again, the intercepts stay the same. Okay? So use the graph x to the third power. So x to the third power, 1 and 2 would be 8. So this is going to be hard to see because there's not that many points. Okay, so we have our graph right here. If I'm going to shrink this, because it's a 1/2, I'm going to shrink this by a factor of 1/2. This point stays the same. This point gets pulled closer to the x-axis by half. This point was 8, and now turns into 4. The next point would have been 327, so it still gets pulled closer, but it's still off the graph. So again, this was not a great graph to look at, but you can sort of tell a little bit. My drawing's not great, but you can sort of tell that it does get a little bit flatter, right? Especially in that area right there. This one will be much easier to tell. So if we have our parent function, okay, my new function, 2 times the absolute value. This one stays the same. Every point gets multiplied by 2. That was 1, 1. It now turns into 1, 2. This one was 1, 2. It now turns into 4. This one was 3. It now turns into 6. Every point gets multiplied by a factor of 2. And in fact, the slope of this line is now a 2. And then the slope of this line is, again, the opposite, which would be -2. So much easier to see with the absolute value function that you're pulling this function away from the x-axis. All these points are not being shifted up the same. They're all these outputs are being multiplied by 2. The 5 turns to a 10. The 10 would turn to a 20 if it was on the graph. Okay? Now, horizontal stretching and shrinking does similar. Look at this picture carefully. You're pulling the graph vertically. You're smushing the graph vertically closer to the x-axis. With horizontal stretches and shrinking, you're pulling the graph closer or further away from the y-axis. And the things that we are multiplied by are now going to be inside the function, and numbers bigger than 1 shrink it. Numbers between 0 and 1 stretch it. You shrink it because you are going to be dividing each x coordinate. You're going to be dividing each x coordinate by the number c. You're going to shrink it by a factor of 2 or whatever, the factor of c. Okay? For vertical stretches, right, we multiplied each y coordinate by c. For horizontal, we're going to divide each x coordinate by c. Okay? And you can tell which one you want to do based on where the number is. Okay, so this is now not a normal function. This is looks like a parabola and a absolute value function smushed together. Okay, whatever. All we need are the points, which we have them. Okay, this point is going to stay the same. Every x coordinate is going to get divided by 2. Okay? So when we graph this, we are going to take every y coordinate is going to stay the same, but instead of being negative 4, 0, it's now going to be negative 2, 0. Instead of being negative 2, 4, it's going to be negative 1, 4. 0, 0, we're going to stay the same. Here, instead of being 2, negative 2, we're going to be 1, negative 2. And finally, the 4, 0 turns into 2, 0. And the shape stays the same because I didn't graph all the points in the middle, right? This point is this one is a curve, and this one is my my V. Okay. So what happened is I took all these points and it smushed it closer to the y-axis. Let's try that one again, except this time with a half. So when you divide by a half, right? When we divide the x coordinate by 1/2, we have the effect of multiplying it by 2. So that means instead of negative 4, 0, we have negative 8, 0. Then negative 4, 4. 0, 0 stays the same because I still divide 0 by 1/2 and nothing happens. 4, negative 2. And finally, 8, 0. And so now my graph looks like this. And what happened is now it pulled it out. It pulled the graph away from the y-axis. The intercept stays the same, but the other points shift. Okay. I don't think I did the checkpoint. Good. Let's do the checkpoint here. Okay. So I have another weird looking graph here. Okay. Let's do a 2 and a 1/2. Okay. So with the 2, I'm cutting all these points in half for the input. So that would be 3. This would be 1, 2, negative 3. There we go. And 3, 0. So we would get a graph like that. Okay. With the 1/2, we'll do this one in red. It would look like negative 4, 0, 4, 8, negative 3, and 12. So now this is much more spread out. Okay. And then we could do other things to this, right? We could move it up, down, left, or right. We could do other sorts of stretches and compressions. We could do reflections. We could do anything we want. Okay. And as long as we recognize all the transformations that are possible, vertical shifts to the outside of the function, adding or subtracting, horizontal shifts to the inside of the function, a plus moves it left, a negative moves it right, a negative in front of the function reflects in the x-axis, a negative inside the function reflects in the y-axis, a vertical stretch or compression if the output is multiplied by a number, and you multiply each y coordinate by that number to change the function. Horizontal, you divide each x coordinate by c to get your new function. And we should sort of follow the order of operations. Okay, go inside the parentheses first. Horizontal shift first. Then stretch or shrink the function. Then reflect. Then move it up or down. Okay, and again, just follow order of operations to be able to get that. Try one with this one. The same function from before. Okay, except now we're going to do 4 transformations to it. We're going to go right 1, then compress it vertically by a factor of 1/2, then reflect in the x-axis, then move it up 3. All right. So first, we go right 1. So instead of -4, this function then goes to there. It goes to 1, 4, to there, and then to 3, -2, and then to 5. So here would be my first function. Okay, let's get a red. Okay, that's not working. Okay, lots of stuff's not working. All right, whatever, no red. Okay, so next we're going to go 1/2. So we're going to compress this vertically. So that stays, the intercepts stay the same. And so now we have a graph that looks like that. Then we're going to flip it in the y-axis, or in the x-axis. So this comes here. So my graph now looks like, oof, it's getting a little funky. So let's get rid of the ones that are old. And then finally, we're going to move it up 3. So 1, 2, 3, right there. This is old point. 1, 2, 3. The intercept, 1, 2, 3, right to there. My peak, and we have my final graph. Okay, so we just followed all the steps and graphed this sequence of transformations. Okay, let's try this other funky picture from the last checkpoint, and we're going to move it right 1, vertically compress by a factor of 1/3, reflect down 2. Okay, right 1 first. So instead of -2, this function starts at left 1 first. So instead of -2, we go to -3. Then there's my peak. Instead of 2, that's a 1. Instead of having an input of 4, it now is 3. And 6 goes to 5. So this one is a picture like that. We're then going to multiply by a factor of 3. Luckily, these are all divisible by 3. So instead of 3, it's going to compress down to 1. This is the same, down to 1, down the same, because we are smushing this closer to the x-axis. Okay, so there's my graph now, very flat. I'm going to reflect it. Okay, so these are old. And now my final shift is to move it down 2. And we get my final graph. Looks like that. Okay. And there is my shift. So easier to do it one at a time than to try to look at that picture and move it around. But what is actually easier is to graph a function that you know what it looks like already. Instead of some weird function with a bunch of different points on it, graphing a parabola is much easier because I can jump right to the starting point. I know that the middle of the function is going to have a vertex of left 3, down 1. So go left 3, down 1. There's my starting point. Okay, this is the trick right here. Normally, a parabola would follow this sequence right here, 0, 0 from the vertex, 1, 1, 2, 4, 3, 9, right? Just squaring the input. So I could move every point, right? Left 3, down 1, left 3, down 1. But I can just count those steps from my vertex, but I do need to multiply the outputs by 2. So from my vertex here, I'm going to go right 1 up 2 because I'm going to multiply. This is a little confusing. I'm going to multiply this one by 2. So this output would turn into a 2, this one an 8, this one a 18. So from the vertex, I would count right 1 up 2, right 2 up 1, 2, 3, 4, 5, 6, 7, 8, and we're not going to have room for 18 there. And then because this is a parabola, I know it is symmetric, and now I get a nice graph like that. Okay, let's try one more of those with my got it problem, or my checkpoint problem. Okay, so same idea here. Start with the vertex, right 1 up 3, stretch it by a factor of 2. So instead of going right 1 up 1, we go up 2, 2, 4, 6, 8. And that'll be good for this graph because it's skinny. And that was everything for section 1-6, transformations of functions.